Let's take a look at some properties of functions and how that relates to derivatives here. So we're going to look at increasing and decreasing behavior here. Going forward, so with increasing, a function is increasing, or is said to be increasing, when the first derivative of that function has values greater than 0. So if you take the derivative and you evaluate it and you get a value greater than 0, it's increasing. This means that the function gets larger as x increases. So this means that basically the output of the function gets bigger as x gets bigger, and vice versa. For decreasing, that's going to be all of the opposite. So a function is decreasing when f prime of x is less than 0. So when you have a negative value for the derivative. And this means that the value of the function gets smaller as x increases. So now what happens when x is equal to 0, or when the derivative is equal to 0? That is a critical point, or that's one of the places we have critical points. So a critical point is where f prime of x is equal to 0, or when f prime of x is undefined. So if it's 0 or undefined, we have a critical point. So I've got here an illustration of kind of all the main ways that you have critical points. So in this first one here, you see that because the slope is horizontal or flat, we can tell that the derivative is equal to 0. Same thing with this bottom one down here. Because the slope is flat, the derivative is equal to 0. So these two are examples where the derivative is equal to 0. You can ignore what it's saying about local minima, local maxima, that sort of thing. These last three, we have the derivative being undefined. So in these top two, we have a sharp corner. And we learned before that a sharp corner means the derivative is undefined. Therefore, these both have critical points where they have that sharp corner. This last one, E, because the slope goes vertical, that means that the derivative is undefined, and therefore that is also a critical point. So really, we kind of have these first four, because B and C are basically the same. The reason why we have two different pictures is because of something we'll talk about later. But these first four kind of show us all the examples. So you can have the derivative equal to 0 or the derivative being undefined. And then there's two cases where you can kind of see that in one case we have like a peak occurring, and in the other case we don't have a peak occurring. So that leads us right into our next point here, which is that critical points, they are going to identify all the locations where the behavior might change, or if you prefer the word could, like it is possible for it to change from positive to negative. So they are, if there are any peaks or valleys in our graph, like we saw previously, we had a peak in A and a peak in B and a valley in C. Those have to occur at critical points. So they must occur at these critical points. However, critical points do not have to be a peak or valley, as we saw on that previous slide here. D and E don't have a peak or a valley, but they are still a critical point. So critical points tell you all the possible places that your minima and maxima could occur if you're looking for those, but they're not guaranteed to be minima and maxima. Because we had that behavior again where it was kind of this curve, or this other curve that I'll sketch here in a second, or this curve. Both of those are examples of critical points without minima or maxima.